So I still feel somewhat compelled to continue talking about level curves for at least a little bit. Um, it does seem like something that's fairly important that your instructor is interested in you knowing about. We've had a few examples here we can talk about. Sure. I will say, Professor Lewis, I do think that he is very much interested in you understanding like what these things mean in the context of the like I forget what examples he was doing. I was looking at the lecture notes, like in the context of where'd he go? It's just there. Like the dose response curve example that he's talked about in class. I do think he's really kind of utilizing that example to help you understand, oh yeah, you have this function of both the dose of the toxin and the weight of the person. And you can kind of hold one of those things constant and think about how changing the other variable changes what's happening. I'm just looking at the notes right here in case you're curious. I was, of course, it zoomed away from where I was. Sorry, it's happened to you. Things right here. But like looking at this example here, right? You've got this function that's a function of the dose and the weight. And then scrolling down a little bit, you can see here the thing that kind of, so some of these functions are kind of the way we look at them depends on the context, right? For this function, it makes sense to think about, well, if I hold a person's weight constant, because for a particular individual, their weight, at least, at the moment, isn't like rapidly changing. But you can think about a person who weighs as much as I do and give them, a dose that's lesser or greater and kind of see how that response curve looks based on their different weights. So then we kind of graph these different level curves for the different values of the weight. Thank you. So that's kind of contextually what we were talking about when we were talking about level curves. Say, yeah, I want to know what's happening at this weight or this weight or this weight, or in the topographical map, how the surface looks at this elevation or this elevation or this elevation, right? If you're getting closer to a peak or some valley or some saddle. In fact, that's kind of actually what I wanted to draw for you as a saddle. So let's talk about some more level curves. We'll try not to spend too much time on level curves because I will say really frankly, graphing a level curve is something that you need to do for yourself, really to really be able to do it. And actually, I'm going to show you one other thing that I think is helpful. So we'll do this example, and you'll see how not lovely my picture is. It'll be fine, but certainly you have tools. I will say it every time. You should use them. Use the tools. Yeah, I part of it is I am very jealous that you have this amazing Desmos 3D tool to graph three-dimensional surfaces that I didn't have when I was a student. I was like, oh, you can just graph the 3D things super easily. You're very lucky, I think. But let's first, we're going to graph the function f of x, y equal to, which way do I like to do it? Yeah, sure, we'll do y squared minus x squared. This is kind of one of your classic examples. We're a little off kilter here. Sorry, one second. There we go. As usual, if I'm off, just let me know and I'll fix it, meaning either tilted or you can't see what I'm writing. So we'll start by graphing some level curves. And the level curves here are interesting. So I should pause. He's talked about traces, right? It's okay if he hasn't. I'm assuming he's talked about traces. So I've said the word trace a few times. When we talk about a trace, that's what's happening in any one of the three coordinate planes. So either the XY plane, the floor, the YZ plane, the wall behind me, or the XZ plane, the wall to your left, assuming that that point down there is the origin of your three-dimensional coordinate system. We want to kind of see what the 2D picture looks like in each of those three planes, and then kind of like superimpose them on top of each other to make it look like the 3D graph you're trying to graph. It's not going to work super great for this one. Actually, you really do need some more level curves. Yeah. So let's talk about the traces first, though. So one, the traces. Here, especially the trace in the XY plane is kind of weird. So in the XY plane, we're going to set z equal to 0 or the function equal to 0. Right? The function is just another name for z, or z is another name for the function. So we're going to get 0 equal to y squared minus x squared. And if I bring the x over to the other side, or the x squared, I've got x squared equal to y squared, which either gives us y equal to x, nice straight line, or y equal to negative x. Really what's happening here is when you square root both sides, you get the absolute value of x equal to the absolute value of y. So another way to think about this is just either x and y have to be the same, right? 3 squared equals 3 squared, 5 squared equals 5 squared, or x and y have to be opposites of each other. 5 squared equals negative 5 squared, or negative 3 squared equals positive 3 squared, right? X and y can either be the same value or the opposite values. That exactly corresponds to the lines y equals x and y equals negative x. So the trace here in the xy plane is kind of funky. It's just this line as well as this line. Yeah. All right, let's continue on. We'll come back to that. That's kind of the weirdest part of this graph, actually. Let's look at the other two traces. In the YZ plane, we have x equal to 0, and we're going to get z equal to y squared. Cool. We know what that looks like. It's your usual upward opening parabola. Again, when you're drawing the traces, you're typically picking the z-axis to be the vertical axis and either the y or the x-axis if you're using zy or zx as the horizontal axis. In a similar but not exactly the same way, in the xz plane, where we're setting y equal to 0, we're going to get z equal to negative x squared. So we're going to have our usual parabola, except it's opening downwards instead of opening upwards. Sorry, that's an x and a z. Apologies. And at this moment, if we were to try to kind of superimpose these two things on top of each other, you're going to have like a parabola opening upward this way. You should look at me for a second. And then another parabola opening downward this way. And then in the xy plane, it just doesn't seem like it's going to make a very nice graph when you put it all together. So we might need a little bit more information. So we're going to find some level curves. We're also going to find, I don't know if this is a good word. I guess level curves in the other direction. So usually when we talk about level curves, it's different elevations, right? You're setting z equal to like 1 or 2 or 3 or -1, right? Some values other than 0. Whereas when you can also look at what's happening if you shift either like to the right or to the left or to the front or to the back by setting either x equal to a constant or y equal to a constant. So we'll look at that as well. So let's look at the level curves first of all. The level curves. So for example, we're going to set z equal to 1. If we do that, we're going to have 1 equal to y squared minus x squared. And this is a classical graph shape that your teacher, at least on paper, expects you to know. Although he might be like, yeah, but they probably don't really know that one because like people often don't know what this graph shape looks like. So this is what's called a hyperbola. It looks kind of, I don't really want to say this, but I'll say it. So it's not. It is not two parabolas, but it kind of looks like two parabolas opening away from each other. But they're not parabolas because parabolas don't have any asymptotes. Any horizontal asymptotes, any slant asymptotes, any asymptotes. But this hyperbola that we're going to draw does have two slant asymptotes that kind of bound where it can be drawn. So here's how I'm going to draw this. I'm just going to let x equal 0 for a second. And if x is 0, right, or I should say I'm finding my intercepts. If x is 0, I'm left with 1 equal to y squared. So y is going to be plus or minus 1. So I have an intercept at 0, 1 and at 0, -1. This hyperbola will not have any x-intercepts. And that's very typical of hyperbola. It either has x-intercepts or y-intercepts. And then, this is where things get kind of messy. We could plug in more points, right? For example, if we let x equal 1 or -1, we're going to get 1 equal to y squared minus 1 squared or -1 squared is still 1. You add the 1 over there, you get 2 equal to y squared. You get plus or minus the square root of 2 is equal to y. So if we go over 1 for x, we're going to go up to either positive root 2 or negative root 2. And that's true whether we're going right or whether we're going left. Already, we got a lot going on. but it's kind of showing us the shape. So down here, we've got this kind of hyperbola shape. Again, not exactly parabolic, but kind of would remind you of what a parabola could look like. And the same symmetrical shape up top here. Oh my goodness. I'm not great at drawing them, in case you hadn't noticed. So there's one of my level curves. If we go up to a height of z equal to 1, this 2D curve is opening on the y-axis, left and right. Right, left and right, because the y-axis is the one that's left or right in the three-dimensional system. And then we could continue doing this. So I'm going to do one more. Yeah, one more. So if I let z equal 2, same sort of thing. 2 is really 2 the choice you want to make, James? Yeah, it really is. I'm gonna do it in a slightly different color here. So let z equal 2. I know black doesn't look a whole lot different than blue on this page, but if z is 2, then we have 2 equal to y squared minus x squared. And again, if I want to find the y-intercepts, well, if I set x equal to 0, I'm going to get y equal to plus or minus root 2. So now, here are my new intercepts. And then it's going to have the same sort of shape, opening away from the origin. I could pick another value. I don't really want to, but if just I will. If we let x equal plus or minus 1, we're going to get 2 equal to y squared minus 1, 3 equal to y squared. We're going to get y equal to plus or minus the square root of 3, which is a little bit higher up here. So same sort of idea. And again, I've probably gotten too much detail at this point, but couldn't help it. And then you can kind of keep going. So it wouldn't be unreasonable to think the higher up we go, just the further out our hyperbola is going to start. And I guess I could label these. This is z equal to 1. This is z equal to 2. Just going to draw one more in here. Here's another one. Again, depending on what your goal is here, drawing these is probably not super helpful. It might be much more helpful to just do some investigation on your own, meaning we can graph these things really easily, right? If I want to graph y squared minus x squared equal to 1, there you go. So see how it's really not parabola looking? We kind of draw it parabola looking, but really it's much more exhibitive of the slant asymptotes, which in this case are y equal to x and y equal to negative x. And then you could go, ooh, here's a cool thing we could do. Instead of like doing this, just seeing it's further and further away, you can do this kind of cool thing where you say it's equal to pick a letter, and then you can add a slider. And then you can just be like, oh yeah, look, if b is larger. This is actually a perfectly good way to draw the level curves, right? Because the whole idea is you're setting z equal to different values in the range. And we can even be smarter about this and pick a step size of 1. But let's not start. Let's be smarter about this, James. And then a step size of 1. And then b could go from, I don't know, -10 to +10. And then if we do that, we can just kind of slide it along here and see, yeah, look, we've got hyperbolas that just move further and further away. So as you go higher and higher up, your hyperbolas move further and further out. And if we let z equal a negative number, I should have just picked z instead of b, whatever. Look what happens. It flips. If z is negative, your hyperbola is open the other way because then you can't find a y-intercept. You can find an x-intercept. So showing you what I mean by that, just to show you one example, if we were to let new pen, we let z equal -1, we would end up getting -1 equal to y squared minus x squared. I almost never like to write this with a negative, so I would probably rearrange it as x squared minus y squared equal to +1. And then you're going to get x equal to plus or minus 1 as your intercepts. And then you're going to open further left and right instead of up and down. So here's my hyperbola when z is equal to -1. And if you go further down, the hyperbolas are going to move further out away from the origin. Okay, so that kind of helps. That kind of shows what's going on. I'm going to do one more thing to help us really see what the graph looks like. I'm going to look at what happens. Well, in fact, I don't think it's even hard to see what happens. If we move, instead of moving up and down, if we move left and right, like setting y equal to 1 or -1, or if we move forwards or backwards, setting x equal to 1 or x equal to -1. But it shouldn't be a surprise because we already kind of saw what happened when x was 0 and y was 0. So just to look at some other, I don't really know a good name for this, some parallel traces, I guess. If you let x equal 1, I'll remind you our equation was z equal to y squared minus x squared. So if you let x equal 1, you're just going to get z equal to y squared minus 1. So we're just shifting that parabola down by 1. So our original, right, x, y, z plane was x equal to 0. We got this parabola here. And then this new one, if we move 1 to the right, we're going to shift that parabola down, right? It's going to lower by 1. We're going to get z equal to y squared minus 1. And then we can keep doing that, right? If we let x equal to 2, same sort of deal. We get y equal to z equal to y squared minus 4. Now, really, I should say this is true whether you pick x equal to 1 or -1. So if you go 1, well, I was saying left and right. Sorry, I meant front and back. If you move front or back, right, I'm always thinking of x as the front back direction, y is left right direction. So if x is 1 or x is -1, your parabola is going to be a little bit lower. And finally, before we start to put the whole thing together, if you let y equal to plus or minus 1, you're going to get z equal to 1 minus x squared. Or as I would probably think of it, z equal to -x squared plus 1. So it's that downward opening parabola, but shifted up by 1. Okay, here is the more important question. Have I done too much work? Probably. But I'm trying to show you all the things here. So definitely, if you're graphing something like this, you probably should be doing way less than I'm doing. Okay, we're going to try and put it all together. So we know that if we move up and down, we get hyperbolas opening either this way or that way. If we move left or right, we get either parabolas that are, if we move front and back, we get parabolas opening up, but have moved down a bit. If we move left, right, we get parabolas opening down, but have moved up a bit. Okay, we'll try to put it all together. Fortunately, well, I shouldn't say anything. I'm going to jinx myself by saying anything. So let's try and draw the whole thing. Oops, see, I already missed there. Okay. So when graphing something in 3 dimensions, if you have options, I would always choose to graph what's in the YZ plane first because that's what's like flat on the paper. You don't have to change your perspective at all. So we know in the YZ plane, we had an upward opening parabola. So let's draw that part first. Cool. And then in the XZ plane, a downward upward parabola. That's the plane that's kind of sticking out towards you. So it's going to get kind of tilted a bit and it's going to look less large. So sticking out towards us, we have that parabola there. Okay, now come the level curve. I'm not, so definitely for this one, I never draw what's in the XY plane. Like it never, ever, ever, ever has looked good ever, anytime I ever tried to draw it. In fact, I'll graph it for you in 3D here in a minute, like on Desmos. It doesn't even look good on Desmos, and it's like perfectly right on Desmos, in my opinion. So I know that if I go up 1, my level curves are hyperbolas opening in the Y direction. Right? We set z equal to 1. We got those I know it's been like 5 minutes since we did that, but we had hyperbolas, holy smokes, opening on the y-axis. On the y-axis, but now the y-axis is this way. So here's what we get. We get a hyperbola that's opening that way, like that. And the same thing over here. But it's like flat. So then I'm going to kind of go past that, and I just kind of go up here and say, cool, I know up here for some other higher value z, I also have hyperbola that opens that way. hyperbola that opens that way. Ooh, I didn't mean to smear it like that though. Same deal over here. I should say that's over here is the rest of this hyperbola. And then if I go in the downward direction, instead of going up some values, if I go down, I still get hyperbolas as my level curves, but instead of opening left and right, they're opening front and back. So this one's a little harder to draw, but like here, essentially, there's a hyperbola that's opening up towards you, and also back here, away from you. Okay. And now we try to put it all together to make it look pretty. So watch this. It should come together all right. Show a little bit more over here, more over there. It looks like a saddle because it literally is a saddle, like the kind of saddle you put on a horse. That is what this shape is. Or if you've ever been out hiking, if you like hike up to like where you go over the hill, but then you decide instead of going over the hill, you can either turn left or right and go up like to a higher peak. That's also called a saddle. There's no other, there's like some dumb name for it in the book. I forget. It's like a parabolic hyperboloid or it's a saddle. Don't call it some other silly name. It's a saddle. Yeah. So you can imagine like your left leg here, your right leg over there, you're facing that way. I like drawing. This is like one of the only shapes I can kind of draw decently, so that's why I also like to draw it because I'm like, oh, it looks pretty good. But let's actually see what it looks like in Desmos because I do think there's some things worth seeing here. So let me grab this here. Also, if you're on Zoom and you have a question, you're welcome to either unmute yourself and ask it, or you can also write it in the chat. I will probably eventually see it. So let's graph this thing. Z equal to y squared minus x squared. There it is. Kind of looks like what I drew, right? I mean, you can kind of see it from that perspective there. Also, you can see in the xy plane the y equals x and y equals negative x level curves you would have just from the shadows there. Also, you can see what some level curves look like by just setting z equal to some other values. Like if I set z equal to 4, you can see, oh yeah, look. In fact, I can do this the smart way. A level curve looks like the up and downward opening hyperboloid. Whereas if we set z equal to negative 4, you can then see down there, oh yeah, it's this other way opening hyperbola going left and right instead of up and down, or I should say 40 backwards. And then also you can also see the level curves in the other directions. If we set, say, like x equal to 4. No, I don't. I actually don't. So we can kind of see it. Yeah, I guess I do want to extend it. Fine. You can see, ooh, if I zoom out a bit, you can see that parabola right there of where that plane is intersecting the surface. That's what a level curve is. When a plane parallel to one of the three coordinate planes, usually the xy plane, intersects the surface that you're talking about. That's the level curve. And then if I let y equal to 4, you can see this. Ooh, can you see it? Maybe. Yeah. I feel like I did something. I feel like I didn't. I don't know what I did. I feel okay. I see. There's my downward opening parabola right there. So all the level curves we talked about, all on your surface there. Okay. So I feel like I've said all there is to say about this particular example, but I should pause and ask if there are any questions about what we've done. We'll try to look at a few more examples with less detail. It's hard for me to do less detail because I feel compelled to like say all the things, but I'll try to say less things about these next examples because the point is really to be able to look at a function of two variables and to get a good working idea of what the surface looks like without doing all of the things that we might be doing here. So let's see, where are my other examples here? Not that one. Maybe that one. Let's look at this one. This one's kind of funky. So let's say our function is something like this. F of x, y is equal to, yeah, x plus 8y over 5x minus y. So we're going to do a couple things here. We're going to do the usual kind of things a web work question would ask you. First of all, we want to find the domain. And I would say, even if you're not explicitly asked to, you should still think about what the graph of the domain looks like. Because the domain for these functions of two variables is all these points in the xy plane. So for this function, just like back in 17a, when I'm thinking about domain, I'm just looking for the three typical problems. Do I have a square root? Do I have a logarithm? Or do I have division? Those are the three issues that give us restricted domains. I don't have a square root, I don't have a log, but I definitely do have potential division by zero. So I need to make sure that we exclude 5x minus y equal to 0. Or in other words, we don't want to include y equal to 5x. So we're excluding that line. Any point on that line is no dice, but every other point in the whole entire xy plane is valid. So writing the domain always feels silly in that you literally just say it's the set of all points such that you meet the criteria you just wrote. So you could write the words exclude y equals 5x, or you could just more easily say all points x comma y such that y does not equal 5 times x. That part's never exciting. The exciting part, the interesting part, is actually graphing the domain. So here we want to exclude the line y equals 5x. So we're going to draw the line y equals 5x, but since we don't want to include it, we're going to draw it as a dashed line instead of as a solid line. And that's the only thing we're excluding. So it's going to be kind of funky. Let's see, here's 1, here's 5, sure, right about there. Does not have to be perfect. So there's my one line of points that we're not including in our domain, and here's our domain. All that. Everything that's not on that line. That's our domain. I know. Kind of funky. Yeah. Let's talk about range. Range always feels even dicier. Dicier? Maybe not dicier, but certainly dicey-ish. Also, I have no idea what this looks like, right? Like some of the times, like a function is kind of typical. This is a very much like a just here's the thing, and maybe we'll try to get an idea of what it looks like. So for the range here, here's a game I play with myself when I'm trying to find the range. I'm gonna look at this. That game is not gonna work here. So here's the game I was gonna play that's not gonna work. Often what I'll do is I'll say, let's set x equal to 0, and then see what I can get by setting y equal to different values. But here that's not gonna work because if x is 0, I'm left with 8y over negative y, which is just gonna give me negative 8. Right? 8y divided by negative y, the y is canceled. And similarly, if I set y equal to 0, x over 5x is just going to give me 1/5. So that doesn't really work here. So here to find the range, you kind of really have to ask yourself the question, okay, if we set our function x plus 8y over 5x minus y equals to c, are there any values of c that we can't get? Oof. Well, here's what we're going to do. We're going to pretend like we're not doing that. We're going to pretend like we're just trying to, what's the word I'm looking for? We're trying to graph the level curves. So, right, this is also what we do when we're trying to see what the level curves look like. Is we set the function equal to a constant, and if we try to make our lives easier, we don't just do like 1 and then 2 and then 3 and then 4. We don't want to do that 4 times. We set it equal to c, isolate y typically because we usually like to graph y as a function of x, and then we kind of ask ourselves, okay, what kind of things do we get here? So hold on to that thought. We're going to do that to see what our level curves look like, but then we're going to answer this question instead. All right, so solving for y, x plus 8y equals c times 5x minus y. Distribute the c. X plus 8y equals 5cx minus cy. Group the y's on the left. 8y plus cy. Group the x's on the right. 5cx minus x. Factor out the y. I don't really need there's no reason to factor out the x on top, but you could. or I should say on the right, not on top, but it's going to be on top. And then we end up getting y equal to 5c minus 1 times x. And I was writing the x in front before, but I changed it. Not for any good reason. Over 8 plus c. So, question. We said the function could equal c. Based on what we have over here, is there any value of c that wouldn't possibly be valid? Totally, -8. So, but I will point out any other value of c should be okay, right? If c is 2, you can pick, plug in c equal to 2, plug in 8x equal to whatever, and you'll find the corresponding y value. So, in fact, let's actually do that. So, for c equal to 2, there's certainly an xy input into your original function. Sorry, I can't quite say that. Right? If you set this original function equal to 2, you can find an x and a y that's going to give it to us. Let's see what so if c is 2, I'm going to have y equal to 10 minus 1, that's 9x over 8 plus 2, that's 10. Pick anything for x you like, 1, and y is going to be 9/10. Or pick x equal to 10 and y will be 9. Or pick literally lots of choices. The point is that there is a point, x comma y, that will give you that output value of c. So here, for example, 10 comma 9, if you plug that into your function, f of 10 comma 9 is equal to 2. So hopefully that kind of shows you that aside from -8, we can pick an output of any value we want, and there has to be an xy coordinate, at least one, probably many, that give you that output, meaning that output is in the range. So now we should address the question of -8. Well, in fact, we already know we can get -8. We talked about it already. We talked about how if I set x equal to 0, then whatever y is going to be, 8 times y divided by -y is going to give you -8. So for example, if you set x equal to 0, and y anything other than 0, right? Because you don't want to pick a point that's not in the domain. But if you set x equal to 0 and y equal to 1, then you're going to get f of 0 comma 1 equal to 0 plus 8 over 0 minus 1, which is -8. So all this work to show that this function has a range of every possible real number, which kind of feels like a lot of work to get that, but sometimes you got to do the work to see the thing. So here, this function, let's just write it right here, is, sorry, I keep moving things around. The range here is everything from -infinity to infinity. Okay, let's go back to the, well, not back to, let's continue on with the question that we've almost already answered already. What do the level curves look like? Yeah. So, level curves. So I'll remind you, we can set c equal to anything. So c can be any real number. We already know what our level curves look like, actually. Well, I should say, we already know what the equation for our level curves looks like. The equation for our level curves is right there. Y equals 5 times c minus 1 times x over 8 plus c. It might be more helpful if I write this in a way that was a little bit more obvious. Y equals 5c minus 1 over 8 plus c times x. C is some constant. What kind of graph does that have? Y equals some multiple of x. It's a straight line. It's a straight line that has what y-intercept? Well, there's no plus b over here, or if there was, it'd be plus 0. This is a straight line through the origin. And I'll say one more thing. If c happens to be -8, your slope would be undefined, meaning you have the vertical line through the origin. And if C happens to be 1/5, you have a slope of 0, meaning you have the horizontal line that goes to the origin. So that's why -8 really is valid here because, oh yeah, we're just getting the vertical line, but the slope is undefined. So that's why it's kind of weird. So we get all lines through the origin. They're not parallel to each other, right? Because they all cross each other at the origin. But you kind of have just so unfortunately, I have no idea what this graph looks like, other than what I feel like, and again, I don't really know. I feel like it's some sort of weird like spiral staircase kind of thing, right? Because like at some C value here, you have a straight line through the origin, and then if you move up, it kind of rotates a bit. Move up, it rotates more. That's what I'm imagining is happening. But we don't have to imagine. Let's take a look. Have I said before how cool it is that you guys have these graphing tools available to you? I might have said it once or twice. Really, 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 truly, you should use this just on your own. Like, it is neat to look at these graphs sometimes. Also, if you ever want to like ask me about like how do you like, there's lots of cool things you can do that you might not think of at first, but you should just put stuff in there and try things out. It's more, I should say, the 2D version has more kind of adaptability. Like you can do more things. Here, the 3D version, you have to be a little more careful about like inputting things in the right way. I mean, nothing bad's gonna happen if you put something in the wrong way, just to, won't get a picture, right? It's not like it's gonna blow up or something. What do we have here? So our function was z equal to x plus 8y divided by 5x minus y. Okay, so I kind of maybe was a little bit on the right track. So definitely you can kind of see here, uh, I mean, it's a neat looking graph. But you can kind of imagine, oh yeah, if I move upwards, there's going to be like a straight line that's like essentially kind of tangent to the whole surface the whole way through. The straight lines are hard to draw. At least they're hard to draw on like Desmos 3D without having a little bit more intuition of where they live. So yeah, but actually let's do ourselves a favor here. Oh, I hate when it does that. There we go. So if we do something like say like z equal to 2, you can see, oh yeah, look, it's exactly crossing that surface or intersecting that surface in a straight line through the origin. Or I should say through the point that is 2 units above the origin, right? Because it's going through 0, 0, 2, not 0, 0, 0. And then if you move up a little bit, oh, we can do something that makes it a little bit easier here. If we go up to say z equal to 3, if you make these translucent, it's a little easier to kind of see the differences. There we go, translucent surfaces there. Yes. A little easier, not like you can kind of see, kind of. Ooh, oof. Sometimes weird things happen. Oh wow. Okay, okay, okay. Calm down. So yeah, you can kind of see your different level curves. There's different planes there, and if you go that way, you can kind of see, oh yeah, there's one there that's behind it. There's one here that's the one you're seeing right there. So you can see these lines like tilting a bit as you go higher and higher and higher. Could I draw this? No, I couldn't draw this. Should we draw this? No, you shouldn't even try. This thing is terrible to draw. You should never be this. Yeah, we shouldn't be drawing a lot of these, in my opinion, personally, because why would you draw a thing terribly when you have a nice tool to draw it beautifully? But I think more the point is to be able to identify kind of some features of these surfaces based on all the information we're gathering. Um, yeah. Let's see. Do I want to torch you with another example? Not really. Yeah. So I should back up. I should say all these lines go through the point x equals 0 and y equals 0, not z equal to 0. So when I'm talking about level curves, my origin is the two-dimensional origin on the xy plane. That's what I mean there. But you're right. We're setting z equal to different values to get those. Although I do think, I have to think for a second here. We can, so we do get a line that goes through the actual origin though, because if we set c equal to 0, so if c is 0, right, the same as saying z equal to 0, we do get the line y equal to 0 minus 1 times x over 8 plus 0 times x. So there is a actual level curve that goes through the true origin 0, 0, 0. But again, that's not what I really mean when I'm saying this. I'm saying on the XY plane, because that's where we're usually drawing our level curves, right? If I set C equal to 0, I'm going to get, okay, I'm going to try and draw some of these. Hopefully they don't look too terrible. Here's my level curve for C equal to 0. And then if I set, say, let's pick another, if C equals 2, go a little bit higher, my level curve is going to be Y equal to 9 over 10 times X. So then over here, right, that's almost a slope of 1. So it's kind of like, there's my level curve if I go up to a height of 2. And then if I set C equal to, I don't know, let's pick something crazy like 4, you're going to get Y equal to 20 minus 1 is 19 over 8 plus 4 is 12. So that's a slope of, I don't know, like 1.5-ish. So, right, so it's going to look kind of like this. So you can see that we start at the ground, our slope's like this, and then as we move up, we rotate to a different line that still goes through the origin, meaning the point x equals 0, y equals 0, and z equals whatever z value we've happened to have chosen. No, we do have one of them. It is this one right here. Because this level curve, where c, aka z, is equal to 0, this level curve does go through the point x equals 0, y equals 0, and z equals 0. Wait. What's our domain? Oh, you're so right. I thank you so much for fixing my very wrong mistake. Oh, thank you. I'm so sorry. Yes, she is very right. 0, 0, 0 is not in the domain. I was just totally forgetting about the original function. So all of these level curves should have the origin. Yeah, should have the origin removed from them. So every level curve I've drawn here should have a hole at the origin. Thank you so much. I feel like I was definitely not hearing what you were saying, obviously. Yes, right? Looking back at our domain here, we don't get anything where x and y are equal to 0. Yeah. Yeah. Good. Very, very, very astute, good observation there. Thank you for insisting that I was wrong when I was wrong. I was like, yeah, what do you mean? Of course we get to go through. Yeah, you're totally right. Yeah. So we don't get any of those points here. So technically here, our level curves aren't lines. They're lines with a hole removed. Yeah. Fun. Curious. I'm curious here. Yeah. So I will point out, so I did grab this question from your web work homework, and your numbers might be different. This is problem number 6, and you probably have different numbers. But I'll point out that so one of the questions is the level curves are, and then it's like 6 or 7 different options, and it says like a collection of unequally spaced parallel lines, a collection of intersecting lines or arrays. Technically, they're not really lines, but close enough. Cool. All right. Yeah, good call. All right, and I was asking myself if we're gonna look in. I feel like we should move on. So again, the graphing of level curves and the graphing of 3D surfaces, you should spend some time doing that, but not too much, right? Your time definitely should be spent meaningfully. So do enough. Definitely focus on the things that your instructor has mentioned in class. But let's move on and talk about partial derivatives, because partial derivatives is really a lot, just like in 17a, we did a lot of differentiation. In this class, we will do a lot of partial differentiation. So, partial derivatives. Here's the good news. If you're good at taking derivatives, you'll be perfectly good at taking partial derivatives. It is almost exactly the same thing. There is just a little bit of extra we have to think about. So let's go over here. Yeah. Oh, we can do that. So we are going to try and add some context here to make it worthwhile. So we're going to look at one of my favorite surfaces. So we're going to first graph the surface f of x comma y equal to 9 minus x squared minus y squared. And I'll just say a few things really quickly here. So we're gonna look at the traces really quickly. So the XY trace. I should maybe say one more thing. I didn't mention the domain. I usually should. But here I didn't think about the domain because I looked at that. I was like, well, there's no square roots, there's no logarithms, there's no division. So the domain has no restrictions. So here my domain is, I'll say my domain is not all real numbers. My domain is all points in the XY plane. So like the point 1 comma 3 and 5 comma 4 and negative 2 comma pi and any X and any Y. But I want to emphasize here, those aren't numbers. They're pairs of numbers, which is a different entity completely. So here, if you want to mention the domain is all points in the XY plane. Or alternatively, you could write it as the set containing X comma Y such that X and Y are both real numbers. Totally fine. So the XY trace, we as usual set Z equal to 0. We get 0 equal to 9 minus X squared minus Y squared. We get X squared plus Y squared equal to 9 because as we've said, if you have an X squared plus Y squared, you should isolate that because you're probably going to get a circle. So this is certainly in the XY plane, we have a circle of radius 3 centered at the origin. Let's find the other things before we get going here. The XZ trace, we're going to set Y equal to 0. We're going to get Z equal to 9 minus X squared. That's my downward opening parabola in the X direction. Sorry, in the X direction. And then the YZ trace. Here's something that's often true. Often, not always, but often, the XY trace and the XZ trace are very, very similar, if not exactly the same. And that is true here. If we set X equal to 0, we get Z equal to 9 minus Y squared. So both of those are downward opening parabolas that have been shifted up 9. So here's my XY trace. Here's my XZ trace. And here's my YZ trace. And then we're going to try and put it all together. So we're going to have the YZ trace sitting on the paper, the XZ trace tilted this way, and the XY trace sitting flat, like on the floor. So this one we want to make it sit flat. This one we want to tilt a little bit. So here's how it's going to look. Color. So, sure. Let's go 3 in each direction. Try to make it look kind of nice. So here's my YZ trace first. Nope. 3. Oh, geez. Okay. Well, kind of nice was maybe an oversell there. And then here's my XZ trace. And then here's my circle that's the floor. Yeah, all right. It's looked nicer, but okay, it's fine. So this is our surface, and it doesn't stop at the XY plane, right? It definitely does continue on downward like that. But like any graph, right, you can't draw all of it, so we often stop at a convenient place. So to me, I always think of this as like a hill, right? This surface, if I was standing on the surface, I could either, unless I was at the very top, anywhere I'm standing on the surface, I could either walk up the hill towards the top or walk down the hill towards the bottom, or I could walk around and not change elevation on a level curve, right? If I was on this hill, I just walked the circle all the way around it and it didn't like go up or down as far as my elevation or altitude was concerned, I would have walked along a level curve of that surface. So the question we want to ask now is, yeah, let's pretend that we're over here hanging out at the point 1 comma 2 comma 4. So I'm going to draw this again because I want it to be bigger. I'll try and do a somewhat better job of drawing it this time. So we're going 3 in each direction. Right, because we know that 9 minus x squared has intercepts of 3. And then we're going up 9. Sure, that's about 9. If I was graphing, this, as I'm graphing this, I'll say I'm actually probably inclined to, instead of graphing the XZ trace next, to draw the circle in the bottom part first and then try to make the other parabola like match up. So I'm gonna draw the circle part here. And then there to there, that's gonna be the rest of my other parabolas. Like that, and then like that. That's pretty good. Much better than the first time. Okay, so let's say that we're over here hanging out at the point, right? Pens. So we're gonna go 1 in the x direction, 2 in the y direction, and 4 in the z direction. Which should be a point, right? If x is 1 and y is 2, you have 9 minus 1 minus 4, which is 9 minus 5, which is 4. So we're gonna go 1 in the x direction, 2 in the y direction, and then finally 4 in the z direction. So what's happening here is we're on, oh, I should use a different color here. Let's do that. So we're on the level curve where z is equal to 4. That point, 1, 2, 4, well, has a z coordinate of 4, so it has to live on the level curve where z is equal to 4. You don't have a choice. But now what we're going to ask is we're going to ask, okay, if I'm actually, like, if I'm imagining this is a hill in the world and I'm standing at this point on the hill, what's going to happen if I move that way in the positive x direction? Am I going to go up the hill or down the hill? Well, here's how we're going to answer that question. We're going to look at the curve along that fixed value of y equal to 2. Because if I'm only moving in the x direction, my z might change because I have to stay on this, right? I can't just like jump off the surface. I have to stay on the surface. So because the surface like has different elevations, if I move in the direction on it, I might change my z value. But if I move purely forward, my y value doesn't change, right? I'm not moving left or right. So I'm going to move in this direction. Let me see if I can draw it well here. Maybe. Not my best work. Sorry, there. We're going to move in that direction along that. Well, in fact, let's just do it. If we set y equal to 2, we're going to have z equal to 9 minus x squared minus 2 squared, or that feels very wrong. Oh, no. 9 minus, so then we get z equal to 5 minus x squared. So not surprisingly, because of how we just drew it here, along this fixed value of y equal to 2, we have another shorter, or I should say shifted downward a little bit, downward opening parabola. So now, if I'm at this point right here, and I move in the direction that's towards you, I'm going to end up going down the parabola. So I would expect my rate of change to be negative, right? If I move in the direction and well, I should say, that question we're asking is, how is z changing as x is increasing? Excuse me. Well, z is getting lesser. It is changing in a negative way. It's becoming smaller. So the derivative in this direction should be a negative value. Okay, a lot of talking to do something relatively easy. If we want to find the partial derivative in the x direction, or more specifically said, with respect to x, often when we want to abbreviate that, we write WRT with respect to x. Well, here's what we're going to do. Our function was z equal to 9, z equal to 9 minus x squared minus y squared. And we're going to take the derivative of that. Here's how we're going to write it. We're going to write, yeah, sure, I'm going to do it this way. we're gonna write del z del x. Del is just a curlier looking d. The top part isn't straight though, it's kind of curly. What you should really do is just make it look like it's kind of halfway between a d and a del, so no one ever questions if you're writing a partial or an actual derivative. But like, right, we're talking about the difference between this and this. They look practically the same with good reason. They are very, very, very much the same idea as each other. You're still just taking a derivative. Okay. I don't care so much about the definition, like the limit definition, whatever. You know how to take derivatives. You did the limit definition of the derivative back once upon a time. Here's what you're going to do. What's the derivative of 9? What's the derivative of x squared? Right. Well, then there's nothing. And then, since we're living in the world where y is equal to 2, the derivative of 2 squared is 0. Or I really could have taken the derivative of that instead. But the point here, what we do in actuality is, if you're differentiating with respect to x, we are pretending, imagining that every other variable other than x and z is a constant. Because it is, right? We're asking, what happens if you move in the x direction and you don't let anything else change other than the output, of course? So we're holding y constant. So the derivative of y squared has to be 0 because y is a constant. So then our derivative here, our del z del x, our partial derivative is equal to negative 2x. And then if you want to find out what the slope actually is, you can plug in the point. So we take our partial derivative del z del x and we evaluate it at the point 1 comma 2 comma 4. We're going to get negative 2 times 1, which is negative 2. So at that point, if you move in the positive x direction, your slope is negative 2. I wish I had a little bit more room. So we can also ask the same sort of question if we move in the y direction at that same point. Let's see if I have I think I have a purple. Yeah, purple. Cool. So we're going to do the same thing here. If instead we fix x equal to 1, right? Because we're on the point where x is 1 and y is 2. So we're fixing x equal to 1. We're left with z equal to 9 minus 1 squared minus y squared, or z equal to 8 minus y squared. So that's going to look like, okay, let's see if I can draw this kind of decently here. That's going to look like this purple parabola here. It's okay. Oh, and should be hitting that point right there. So again, the idea is we're just moving along this parabola. And if we start here and we move to the right, we should also see that our slope is going to be negative, but it's going to be a different negative value. Let's find out what it is. So, yeah, I should move down here. So in the y direction, yeah, sure. Okay. So in the y direction, holding x constant, we're going to get that del z del y, had to take a minute there. Well, if we look at our function here, the derivative of 9 is 0. The derivative of x squared is also 0 because we're holding x constant, and the derivative of y squared is negative 2y. So we get del z del y equal to negative 2y. And then if we plug in the point that we're looking at, so del z del y evaluated again at the point 1 comma 2 comma 4, it's going to be negative 2 times 2 because we're plugging in the y value instead of the x value this time. So not too surprising because this parabola is kind of higher up. So when you go this far down, you've got a steeper slope of descent in the y direction than you do in the x direction. Which again kind of makes sense, right? If you've ever actually been out on a hill, right, the direction you travel affects the steepness of the slope you're traveling on, right? You could try to go up the hill in the steepest way possible, or you could do what most people do and like go around the switchbacks and like take your time and try to have a nice day out in the woods. Okay, but that's the main idea is that when you take the derivative with respect to one variable, you pretend like the other variables are constants. And they follow the rules constants. So the two things to remember about constants is the derivative of a constant by itself is what? You all know. But when you take the derivative of a constant multiplied by a function, like for example, in fact, let me just write, instead of saying words, let me write words. So just, oh my gosh, maybe. Sometimes. So as a reminder, if you take if your function is, say, a function of one variable, if your function is, I don't know, sine of x plus 6, my derivative is going to be cosine of x plus 0. Because when you have a constant by itself, its derivative is 0. But if your function is, say, a constant multiplied by some function, the derivative of that constant doesn't just become 0. We have the constant multiple rule, which essentially says constant multiples just hang out. The derivative here of 6 times sine of x is going to be 6 times the derivative of sine of x, which is cosine of x. If you really, really care, what's really happening here is we're using the product rule, and the derivative here is going to be the derivative of 6 times sine plus 6 times the derivative of sine. And then, yes, the derivative of 6 is 0, so that ends up being 0 times sine plus 6 times cosine. And then that part is just 0, so you get that. That's really what's like the intermediate work here. But it always ends up being that when you have the constant multiplied by a function, you just leave that constant out in front and then take the derivative of the function and multiply them together. Okay, so the same sort of thing is going to be true for functions of two variables. If you have, say, f of x comma y equal to sine of x plus y squared, and I want to find my derivative, well, del f del x, the partial derivative with respect to x is going to be cosine of x. On the other hand, if my function g of x comma y was equal to y squared times sine of x, then my del g del x, my partial derivative with respect to x, would be the y squared is just going to hang out as a constant multiple, and the derivative of sine of x is cosine of x. So keep that idea ever present in your mind when you're taking partial derivatives, because it's always true. If you're differentiating with respect to something, the other variables get to be pretend like they're constants. Let's look at some more examples. And we'll talk about some notation as well. So let's say we have the following function. Sure. So we've got f of x comma y equal to x to the 6th plus y to the 4th plus x squared y to the 5th. And we're going to find all the first partial derivatives as well as all the second partial derivatives, including the mixed partials. So, sorry. Notation. There's two typical notations we use. You could either say for the partial derivative with respect to x, you can call that del f del x, the partial derivative of f with respect to x. And again, the way you know it's a partial derivative is that your function is a function of more than one variable. Also, the curly d, the del notation means with a partial derivative. So you only use this notation for a derivative if your function depends on more than just the variable you're using. Or people don't like writing all that, kind of like how you don't want to write dy dx all the time, you like to write y prime some of the time. The other typical notation is fx. So it's f with x as the subscript. We do not say f of x, that is the function f of x. We say literally the words, letters, fx. End of story. That's how you say that. That is fx, that is del f del x. So then if I take the derivative of this with respect to x, I'm going to get 6x to the fifth plus 0 plus 2x times y to the fifth. And I would simplify that or rewrite it as 6x to the fifth plus 2x times y to the fifth. All right, I would like you all to find del f del y, or fy. You should be getting 0 plus 4y cubed plus x squared times 5y to the fourth, which I would probably rewrite as 4y cubed plus 5x squared y to the fourth. It doesn't really matter what order you write the letters in, but typically we write them in alphabetical order. Or the fun way of saying it mathematically, we write it in lexicographic order, which is just a math word for alphabetical. Okay, those are the first partials. Let's also find the second partials. So more notation here. The second partial derivative of f with respect to x is written in the following way. It's del squared f del x squared. The reason that's why we write the notation this way, just like you would write the second derivative for y, right, d squared y dx squared, it's because it's the partial derivative with respect to x of the first partial derivative of f with respect to x. All right, it's just the derivative of the derivative. In the simpler notation, it is fxx. You're just differentiating with respect to x twice. So usually what you would do is you would just look at the first partial derivative fx and then take the derivative of that with respect to x. If you want to write more things, you could write it as like, I don't really want to write more things. You could write it as del. I'll write it. Normally you wouldn't write this. You could write it as the derivative with respect to x of my first derivative, 6x to the fifth plus 2xy to the fifth. I personally think you should skip this. You don't, right? You can see the first derivative there, and then you can take the second derivative and say, okay, the derivative of 6x to the fifth is 30x to the fourth. The derivative of 2x times that constant is 2 times that constant. Right? I'm not even thinking about the y to the fifth other than I know it's multiplied by my function. Let's do the same thing for the second partial derivative with respect to y. So it's either del squared f del y squared, or if you prefer, fyy. Go ahead and look at your first partial derivative and take the derivative of that with respect to y. I should say, look at your first derivative with respect to y and take the derivative of that with respect to y. So I'm getting 12y squared plus 20x squared times y cubed after I've simplified it. Okay, now for the fun, not so fun one. Here's why it's not fun. The notation is unfortunate. So for the mixed partial derivative, there's two of them. Order, right, depending on which one you do first and you do second. So, okay, so here's what we're going to say. We have del squared f del y del x. So what this notation means is you're going to do the derivative twice. The first time with respect to x. The second time with respect to y. So let me point out, this is the derivative with respect to y of the derivative of f with respect to x. Now here's the unfortunate part. The other notation, the subscript notation, we read from left to right. So this is the same as fxy. This notation here, del squared f del y del x, means x first, then y second. This notation here, fxy, means x first, then y second. Kind of a bummer. Here's the good news. Here's the bad news. The bad news is people will want you to do things in the right order. The good news is if you accidentally get it wrong, the order doesn't matter. As long as it's only X, Y, or Y, X, right? If you do X, Y, well, in fact, why am I saying it? Let's just see it. So if we do it this way, so it's going to be the derivative, in fact, so it's del y of our fx, which was 6x to the fifth plus 2xy to the fifth. The derivative with respect to y of 6x to the fifth is 0. The derivative of 2x times y to the fifth, well, the 2x is a constant, and the y to the fifth has a derivative of 5y to the fourth. So here the derivative ends up being 10xy to the fourth. And then if we go in the other order, del squared f del x del y, or del x of del f del y, which is just fyx. That's going to be the derivative with respect to x of the partial with respect to y. 4y cubed plus 5x squared y to the fourth. And if we differentiate this with respect to x, the derivative of 4y cubed is 0. The derivative of 5 times x squared is 10x, and that y to the fourth just hangs out. And look, we get the same exact answer. So you might ask, why do we even care then if you get the same thing every time? Well, because you don't. Here's the good news. I'm saying this a lot. The good news is in this class we never really encounter functions where the mixed partial is different depending on the order you do it. There's something called Clairaut's theorem or something about like when these mixed partials are equal to each other. And the general idea is that as long as the function is normal-ish, I know that's a very, very vague thing I'm saying, but basically to have a function where this idea fails, where the mixed partial in one order is different than the mixed partial in the other order, your function has to be relatively complicated. Like it's some piecewise thing that's like equal to something, sometimes something else, other times. So you shouldn't worry about these not being equal to each other. They're almost always going to be equal to each other, especially in this class. Now that said, your teacher still wants you to do the things in the right order. So like you should definitely, if you're finding fxy, you're differentiating with respect to x first, then y second. It also matters because sometimes we ask, like, for example, I could ask you, say, to find like f x x y x, which you definitely don't want to write the other way. Writing this the other way would be del fourth f of del x del y del x squared, I guess. That seems silly. That's just dumb to write. You shouldn't write that. I shouldn't write that. Nobody should write that. Don't write this. Just say, okay, well, my function is still the same function as before, x to the sixth plus y to the fourth plus x squared y to the fifth, and then just start working through it. So we're going to do x first, so fx. I know I've already done this, but I'm going to do it again. Is 6x to the fifth plus 2x y to the fifth. And then another derivative with respect to x is going to be 30x to the fourth plus 2y to the fifth. And then if I go with respect to y next, fxxy, I'm going to get 0 plus 10y to the fourth. If I do x again, then I'm going to get 0. That wasn't on purpose. It just happened to be what happened. So you definitely do have to do things in order for taking like a really many pieces mixed partial derivative, but just be careful. I would say in general, I would default to this notation because it's just less writing. Okay, where are we at? We got 5-ish minutes left. Let's point out that um, most of the time in this class, our functions are functions of two variables, but they don't have to be. You can have a function of 3 variables or 4 variables or any number of variables, really. So you can take all sorts of partial derivatives. For example, yeah, sure. If my function looked like g of x comma y comma z equal to x to the fourth times sine of 2y plus z cubed. I could ask to find all sorts of mixed partial derivatives. So, but first, usually if you're being asked about partial derivatives, they almost always ask you to find the first partials. So let's go ahead and find gx, gy, and gz. Or if you like, although you shouldn't, shouldn't the wrong word. It's easier to write this, right? I kind of go with this because it's just what I like. So if I'm going to find del g del x, well, I've got my function, I've got x to the fourth times a whole bunch of stuff that doesn't have any x's in it. So as far as I'm concerned, sine of 2y plus z cubed is a constant for the purposes of this first partial derivative. So my partial with respect to x is going to be the derivative of x to the fourth times this constant that it's still multiplied by. For gy, wow, my y's really look like, I feel like that y there looks a lot like a g. Shouldn't, but it does kind of. For gy, which again, if you want, you could say it's del g del y. Now, the x to the fourth is a constant multiple. It's just going to hang out. And the derivative of sine of some stuff, where our stuff does have a variable in it, we have to use the chain rule. Derivative sine of x is cosine of x. Derivative sine of some stuff is cosine of that stuff. And then we have to multiply by the derivative of the inside part. The derivative with respect to the variable y. So the derivative of 2y is going to be 2. The derivative of z cubed is going to be 0. Okay. Same thing for gz. I should say similar thing for gz. Del g del z. The x to the fourth still hangs out in front. The derivative sine of some stuff is still cosine of that stuff. But then when we use the chain rule, multiply by the derivative of the inside, now we're differentiating with respect to z on the inside. So it's going to be the derivative of 2y is 0 plus the derivative of z cubed is 3z squared. Yeah, we should do that too. Should we do that too? Sure, I got one more thing for you. This will actually come back again a little later. So let's say we had something like, sure, x squared. Oh, what? Oh, there's something in the chat. Something in the chat. Why did I'm gonna need more than that? Why didn't you take the derivative of the first one? Like, why didn't I take the derivative of? I'm not sure what you're asking. Okay. So the question is, why didn't I take the derivative of sine of 2y plus z cubed for the first one? And the answer is because for that part, we were differentiating with respect to the variable x. So when I take the derivative of x to the fourth times sine of 2y plus z cubed, as far as the variable x is concerned, this whole thing here is a constant. So it's kind of like, I'm going to write it this way. It's kind of like I have g of x comma y comma z equal to x to the fourth times a constant. And then when I take the derivative with respect to x, it's going to be 4x cubed times still that constant. That constant in this case happens to be sine of 2y plus z cubed. So this right here, this is acting like the constant for that partial derivative, but not for the other ones. So it shouldn't be, no. So it's not 0. So the question is, shouldn't it be 0 then? And the answer is no, because it's a constant multiple, right? If I take the derivative, so over here, right? If I take the derivative of x to the fourth times 6, I don't get 4x cubed times 0. I get 4x cubed times 6 because that 6 multiple sticks around. It might be easier to see if I interchange the order. The derivative with respect to x of 6 times x to the fourth is just going to be 6 times 4x cubed, or 24x cubed. So I'm going to say this again very, very, very emphatically. Constant multiples hang out. They don't have a derivative that's equal to 0. They stick around and they multiply by whatever the derivative of the variable part actually is. Yeah, so in this case, we are treating the entire trig function as a constant when we're differentiating with respect to x, because as far as x is concerned, this sine of 2y plus z cubed is a constant. Y is never changing and z is never changing. If we're asking here, so I should say, here's the question that we're asking when we take this derivative. How is g changing as x changes? And the thing that's not said there is as x changes and y and z stay constant. Right? We're only asking about how g is changing as x is changing, not having anything to do with y or z. So that's what's happening there. And I guess we'll stop there.